Okay, in this video I'm going to help you out with questions 10.3 and 10.4, and then hopefully you can finish them by yourself. So 10.3 says you have yeast cells. That's why they use the letter Y here for the number of yeast cells. Starts off with 10 to the 6, which is a million, right? 10 with a 1 with 6 zeros is a million. So you start off at times 0 with a million, and then it increases at the rate of e to the 0.495105 t power. And e is a natural exponent, which we're going to get into a whole lot more, I think, the next chapter. And it's on your calculator, but e is just this crazy number, 2.71828, goes on forever. And it's going to come up a whole lot. But anyway, it's a common base. So we're using a natural base, e to that power. That's the number of yeast cells we have at any time t we want. So for part A, it's pretty easy. You say how many cells per 1 hour? You just plug in 1. And then your job is to figure out how to make it on your calculator. You go e to that power times a million times 10 to the 6. And you should get over a million yeast cells, because after 1 hour it's probably growing. And so I think you guys can do that. Then they say B, true or false, the population of yeast cells will double every 1.4 hours. Well, plug in t equals 1.4 into that equation. Then go e to that power, e to the 0.495 into 1.4. Again, it's a calculator problem. And you should get double the amount. So if you start off at 1 million, you should get 2 million. You should get about 2 times 10 to the 6. And if you do, then yep, that's the doubling time. 1.4 hours, and if you don't, then yeah, I guess it's not. So all you're doing is plugging that in. Next chapter, we'll learn how to solve for that better. We have to use logarithms, though, which cancels out the e. And since we haven't done that yet, they just had to check that, which is kind of why they said that. And then C is a little bit trickier. They say that Sherry, another member of your lab, looks at your notebook and says that she thinks, no, y is 10 to the 6. Again, you start off with a million cells, but then it's a new base, 2 to the 0.04, and they give a whole lot of decimal places because it matters. A little tiny bit off makes a difference when you have exponents. So that to the 0.693147t, and that's what her formula was. And you had the other formula, this one. Again, this is the A0B to the T, but this is B to the AT, where our A is that thing and our base is E. And so she's got a different base, not E, and a different number up here. And you want to see if they're the same thing. Well, the 10 to the 6 is the same thing. So what you do is you use our rules here, and this is the same thing as 2.042727 to the 0.693147, all of that to the t, because you multiply exponents, so raising it to the t is the same thing as putting the t there. When you want to see, is that the same thing as e to the 0.495105 to the t. So is e to that number the same as this base to that number? So again, it's a calculator problem. You plug in this as the base, raise it to that power. Plug in this as the base, raise it to that power. On whatever calculator you're using, a lot of them, they use a little, I don't know, a little hat symbol. I've heard it called a caret, little caret symbol to also raise something to a base. So you have like the base, put that thing here, and then put the exponent in. So that means raising it to the power. That can help a lot. That can be an easy way to do that. So anyway, that one you're just seeing if that's true. So that's not so bad. So you can do that. And then finally on D, you just plug in the different times, 4 hours, 6 hours, see if you get the same results that this person gets. So basically a calculator problem, which is not easy to always get used to plugging all these things in. Okay, that is number 3, and then going over 10.4 here. And 10.4 is dealing with pianos, and section 10.3 talks about how this works. And it's pretty cool because this is how the piano keyboards work. And basically there's 12 notes and a scale, including the sharps and the regular whole notes. There's 12 notes. So you go from like A, and then it goes to A sharp, and then B, and then C, and then C sharp, and it goes all the way back to A. And before it gets all the way back to A, I guess what's the last one? G sharp. Back to A. There would be 12 of those. So what they do to make it sound good, and what that sounds good to your ear, is every single note is 2. Because, and here's the other thing to know, that if this A here, which is the middle A, is 220 hertz, they tell you that in the book, then the next A is always double that. That way it sounds like the same note to you. If you double the frequency, it sounds like the same note. So the next A is 440 hertz, which means if waves go back and forth 440 times a second, the vibrations are twice as fast, 440. The one below that, the A below 220, is 110. So that will also sound like an A to your ear, but it'll be lower. And the next one, you just keep multiplying by 2. The next A higher would be 880, or the next one A lower would be 110. Now, what about the A sharp and the B? To make it so since there's 12 of them, and we want to make it double, you multiply each one by 2 to the 1/12th power. That way, when we have 12 of these, if you do that 12 times, which means you raise it to 12th power, that means we have 12 of these going on. 12 times 1/12 is 1, and that's equal to 2. And after we do it 12 times, we just double the frequency. In other words, we go from 220 to 440. So every note is 2 to the 1/12th times higher. 2 to the 1/12th, it turns out, I just put it in my calculator, that's about, get off my notes here. It's about 1.059, goes on forever. So every note is about 1.059 times higher, which means that the bigger the frequency, like 440, and then as it goes up, it's a bigger jump in frequencies. So every note you go up higher is a bigger jump in hertz, but it sounds okay to your ear because it's the same ratio. It's kind of crazy. Okay, so that's all you got to do for these problems. So it says find the frequency of middle C. So for part A, if the middle A is 220 hertz, and then it goes A, and then A sharp, and there's a picture in this in section 10.3, which you'll need to look at, and then B, and then C, well, looks like we had to multiply it 3 times. Once, so times 2 to the 1/12th, times 2 to the 1/12th again, times 2 to the 1/12th again, and that will get us that number. So basically you take 220 and then multiply it by 2 to the 1/12th 3 times, which is the same as 2 to the 3/12ths, and that will give you, that's 3 times higher, so that's 3 times higher than middle A. Okay, so again, it's kind of a calculator problem, but you have to understand what's going on to be able to get that. And then it says, find the frequency of the A above middle C. Okay, I kind of already told you how to do that, because if the 1A is 220, the next one's 440, the next one's 880, you just keep doubling every single time. And then they talk about this crazy Bosendorfer piano, which has, C, they talk about, they ask what is the frequency of the lowest note on the keyboard. And if you look at, again, section 10.3 on the keyboard, it's an A. So that means how many A's below, and I'll let you count that. You start off at 220 and you keep cutting it in half. And how many times you got to cut it in half? In other words, how many A's are there below this A on the keyboard? And that tells you how many A's you got to cut it in half. The one below 220 is 110, and then cut in half, what's that, 55. You keep cutting in half until you get to the lowest one. Okay, so that's how you do part C. And then part D, they talk about this Bosendorfer piano, and it's got a C below the A. So once you figure out the A up here, then you go one lower than that one. So you go one lower than that one. So the A below part C, which you just figured out, and then the Bosendorfer's got a C above that. So it's just like you did in part A. You take that A, it doesn't go quite that low. So you go to the A sharp, it doesn't go quite that low. Go to the B, go to the C. So you multiply it by 2 to the 1/12 3 times. So again, you take the A below what you got in part C, divide it in half, and then you got to go 3 times up. So take that A, multiply by 2 to the 1/12 3 times, and that should be this lowest note on that piano. Okay, that's how pianos work, and that's again a use for all these exponent rules, and it's pretty cool. Okay, hopefully that makes sense. Again, let me know if something doesn't make sense or you need help with some of the other problems, and I'll try to help you out. Thanks, bye.